Yeah, very good. So for today's particle theory seminar, we have Emanuel Malek, all the way from Humboldt University in Berlin, and he's going to tell us about Kaluza-Klein spectroscopy for string theory compactifications.
Great. Thanks a lot. It's really nice to be here. Thanks for the invitation, and thank you all for coming on such a beautiful day in Chicago. So I'm going to give a bit of an overview of some of the work I've been doing recently over the last couple of years, which has been focused on computing these Kaluza-Klein spectra for large class string compactifications. And this has been done over a number of years, a number of papers with a large number of people whose names I won't read out, but they're all fantastic collaborators. So let me just briefly set the scene. String theory is a theory in 10 or 11 dimensions. So if you want to learn about some physics in lower dimensions, we need to consider compactifications. So these arise in pretty much all kinds of string theory applications. And whenever we compactify our theory, we end up with towers of massive modes, so-called Kaluza-Klein modes. These come from the fluctuations of the theory inside the compactification space. And from the lower dimensional perspective, these towers of Kaluza-Klein modes are a signature of the fact that the theory actually comes from some higher dimensional original theory on a compactification. And in particular, the information of these Kaluza-Klein modes encodes the geometry of the compactification from the perspective of the lower dimensional theory. So philosophically, these Kaluza-Klein spectra are very interesting, but even more practically, we can use these to learn about some interesting things, in particular in the ADS-CFT correspondence, which will be one of the main focuses of this talk. The Kaluza-Klein spectrum of compactification tells us about the conformal dimensions of operators in the strongly coupled dual conformal field theory. And these anomalous dimensions are something we can typically not compute as strong coupling. And then another application I will also talk about is the stability of non-supersymmetric vacua. Without supersymmetry, we don't have any guarantee of stability. And in particular, the Kaluza-Klein spectrum allows us to at least test perturbative stability of some non-supersymmetric vacua. Okay, so given that I'm going to do a few ADS-CFT applications, I just want to briefly remind you of some features of ADS-CFT. So whenever we study string theory on some ADS background, this encodes information about some conformal field theory living at the boundary of the ADS space. And what makes the ADS-CFT correspondence so interesting is that it's a strong weak duality. So when we have a good control of the string theory, you can learn about strong coupling in the conformal field theory. And in particular, this means that the ADS-CFT correspondence is one of the very few tools we have to actually obtain quantitative results for strongly coupled CFTs. And so there's a few things that we can compute in the ADS-CFT dictionary. So the very basic dictionary relates fields in the gravitational picture in the string theory to operators in the dual CFT. And in particular, if we have massless fields in the gravitational theory, so-called moduli, these correspond to a particular set of operators in the CFT. Particularly, these operators are exactly Marshall deformations. So operators that we can use to perturb our CFT while preserving conformality. Moreover, if we have a family of ADS vacua, so if the compactification has some parameters which preserve ADS, then we have some moduli space of ADS vacua, and this moduli space of ADS vacua will correspond to some space of CFTs known as the conformal manifold, where every point in this space corresponds to CFT, and this might be linked to some original CFT by turning on some of these exactly marginal deformations. So we have this very nice picture. On the gravity side, we have some ADS vacuum times some compactification, and if this is part of a family, then the deformations of this compactification corresponds to deforming the CFT by some exactly marginal deformations. And this is very useful because in the CFT, we can often compute a few things about the conformal manifold, especially if we have supersymmetry, but typically only local properties, properties near some CFT where we have a good understanding. Understanding global properties of the conformal manifold is typically very hard. By instead mapping this problem into some problem of moduli spaces of ADS vacua, we can learn much more about these global properties of the conformal manifold. Okay, so this was one particular set of fields, so-called moduli. Well, generally, if we look at the Kaluza-Klein tower coming from the compactification, then the masses of these Kaluza-Klein towers will tell us about the anomalous dimensions of the dual operators. One very interesting question one could ask, for example, is what happens to these anomalous dimensions as we move around the conformal manifold? So what happens to the masses of the Kaluza-Klein spectrum as we deform the compactification? And this will be the sort of problems I will show you we can now solve. Okay, so let me set the scene a little bit more precisely. I'm sorry if this is very basic. So the setup that I'm interested in is where we study strongly coupled conformal field theories, which means in the string theory, we're interested in the regime where the curvature scales are much larger than the string length. String theory drastically simplifies in this case and becomes 10 or 11 dimensional supergravity, which you're probably all familiar with, but just in case you're not, there's a theory of GR. A supersymmetric theory has fermions and then another set of bosonic fields, which are higher dimensional analogs of electromagnetic fields known as fluxes. And these play a crucial role in everything I will tell you. Okay. So coming back to this question of the Kaluza-Klein spectra, why is this worth giving a talk on? How is this a difficult problem? If you have only met Kaluza-Klein spectra briefly, you've probably seen this example of a free scalar field on a circle where you can compute this spectrum and everything seems nice and simple. So let me just go through the basic example. We have a scalar field phi. It depends on some lower dimensional coordinates x and coordinate y on the circle. It's a free scalar field. This is its equation of motion. So now, because I'm looking at a scalar field in the circle, I can expand my field in terms of a Fourier series, and the Fourier modes phi k of x are some lower dimensional fields. And simply by plugging this into the equation of motion, we find that the Fourier modes obtain a mass k over r. This is very basic Kaluza-Klein tower that probably most people are familiar with. What happens if we try and do the same thing in supergravity? Well, in supergravity, equations of motions are a lot more complicated, even at the linearized level, which is enough to study the masses. Particularly, the equations of motions mix the metric degrees of freedom and the flux degrees of freedom in supergravity in complicated ways. So just as an example, here is one of the equations of motions of 11-dimensional supergravity, has a metric and has a 4-form field strength for the flux. This is the equation of motion you get. It's very complicated. This is linearized around the background with some background 4-form field strength, some background metric that I don't write explicitly. Is the fluctuation of the 4-form field strength, the fluctuation of the metric. And you see they're coupled and mixed in a very complicated way. So it's even unclear how to do some sort of expansion, like a Fourier expansion, and what kind of eigenmodes of this operator to expand, etc. So because of these problems, computing Kaluza-Klein spectra was really only possible in 2 types of situations. If I give you some generic compactification, it used to only be possible to compute the Kaluza-Klein tower spin 2 fields, so the excitations of the graviton.
That's because the graviton doesn't mix with lower spin fields?
Right, so not quite, but the mixing, you can essentially plug back the equations of motion and then absorb all of the mixing into some warping. So you can rewrite the equations of motion in such a way that there is no mixing, and instead there's some warping, so the spin 2 spectrum turns to solving some warped Laplacian. So very simple. Okay. But indeed, that's not the case for the other fields. So if I give you generic background, what used to be possible was just to compute the spin 2 spectrum, nothing else. If you wanted to compute the full spectrum, this used to only be possible on coset spaces, where you have a lot of symmetry. Okay. So this used to be the situation, obviously very dissatisfying. So then there's a third tool that is also very useful and will play an important role in this talk, and this is something known as a consistent truncation. So what is a consistent truncation? It's a truncation where I keep only finitely many Kaluza-Klein excitations, but I keep these to a full nonlinear order. So it's a nonlinear truncation to some subset of KK excitations. This gives me some lower dimensional theory with a finite number of fields. And then this word consistent in consistent truncation is a technical word. It means that we want to impose that all the solutions of the lower dimensional theory are also solutions of the original theory. This is what it means to have a consistent truncation. So for example, there's a consistent truncation of type 2b supergravity on the 5-sphere. So this is the Kaluza-Klein spectrum of the type 2b supergravity on the 5-sphere. These are all the different KK excitations. And there is a consistent truncation where you only keep a full nonlinear dependence on these lowest couple of modes encircled in red. If you do this, you obtain a 5-dimensional maximally supersymmetric supergravity theory. It's very interesting. It's a nonlinear theory, of course. It has a potential. And in particular, it has a number of interesting vacua. What the consistent truncation now allows you to do is it allows you to compute what happens to the masses of the fields that you've kept as you deform the 5-sphere inside this consistent truncation. So I can go from the round 5-sphere, I can deform it a bit, corresponding to going to some other vacuum of the 5D theory, and I can see what happens to these 3 sets of modes that I've kept. But the consistent truncation means that you have no access to the modes that you haven't kept. You don't know what happens to their masses. And in particular, as I will show you, extrapolating results from these lower dimensional theories where you only keep a finite number of sets of fields and you ignore the rest can be very misleading.
So you can get away with not including all the tachyons in the story.
So these are not actually tachyons because it's ADS. So these just.
What about the BFM? I mean,
exactly.
But you have a 50 in there that is not in the consistent truncation.
Exactly, it is not in the consistent truncation. So there's no scale separation if this is in particular what you're asking. So there's, from an energetic perspective, there's no reason to include this field but not this field, and this field, not this or this. And I'll come back to scale separation a bit.
So how do you understand whom should be included?
I will tell you in a second. Okay, so now the crux of this talk is going to be that with Henning Samtleben, we developed a method that now actually allows us to recover the masses of all of the fields that we haven't kept in the truncation for any vacuum inside the consistent truncation. So we can now compute the spectrum around any of these vacua, the full high dimensional theory, as we deform within the consistent truncation. And the key to this is to exploit hidden structures that these compactifications have because of this property of the consistent truncation. Okay, so here's a brief outline. I will tell you a little bit about this formalism exceptional field theory that plays an important role and how it describes consistent truncations. I'll then show you how to compute Kaluza-Klein spectra, and then in particular, how we can learn some nice physics from this. And then if I have time at the end, I'll tell you about some soon-to-appear work where we can generalize this even further. So let me come back to all of these questions about consistent truncations now. In a consistent truncation, we want to keep only a finite number of fields in the full nonlinear way, such that all the solutions of the lower dimensional theory are solutions of the higher dimensional ones. So this requires some typically some very complicated nonlinear embedding. The nonlinear equations of motions make this highly non-trivial, right? As someone asked, how do you know which fields to keep? You don't have, in particular, if you don't have a scale separation. And what ends up being crucial is that there's some sort of symmetry argument. I'll make this very clear. There's some sort of symmetry argument that assures you that the fields that you're keeping won't source fields that you're not keeping. Now, this is a very strange thing to do. It's not what you usually learn to do in physics. Normally, you would look at some low energy effective theory. But this is not, low energy effective theories are difficult in ADS vacuum and string theory. In particular, there's I'll say no well-controlled ADS vacuum of string theory with scale separation. It's an ongoing debate, but yeah, I guess everyone agrees there is stuff to debate at least. Certainly all well-controlled ADS vacua do not have scale separation. So what do I mean? I mean that the lower dimensional supergravity modes are not separated from the other Kaluza-Klein modes by some scale related to the compactification. So there's no way that I can make the compactification small in some appropriate way and have all modes except supergravity modes become infinitely heavy. This doesn't happen in ADS. So instead, if you want to use a low dimensional theory, you have to use this strange beast of a consistent truncation. Okay. So I said you need these symmetry arguments. What kind of symmetry arguments should one use? Well, the very basic example is that of a group manifold. So if I look at a compactification on a group manifold, it doesn't seem very interesting, but I will generalize this in a way that will make it interesting. Then we have a nice symmetry argument from the group structure. So in particular, we have two important features on a group manifold. The first is we have a globally well-defined set of vector fields that define a frame, left invariant vector fields on the group manifold. So as a frame, these define some d by d invertible matrix where d is the dimension of the group manifold. And then secondly, the Lie derivative of these globally well-defined vectors closes into an algebra, and the structure constants are just the structure constants of the Lie algebra of the group manifold. So these two facts together allow one to prove very easily that you will always obtain a consistent truncation on a group manifold. And in particular, what you do is you take all of your fields of the higher dimensional theory, you simply expand them in a basis of this global set of vector fields. And the coefficients in this expansion would be the fields of the vector. And the Lie algebra that appears here, this will determine the gauge group of vector fields of the lower dimensional theory. These are group manifolds, so not terribly interesting. And we know of examples of consistent truncations that are not on group manifolds. So let me show you another example. It's again a bit archaic, but it's instructive. So it turns out that if you look at a theory of gravity coupled to a vector field and a dilaton with a very specific coupling between the vector and the scalar, it turns out that this admits a consistent truncation on a two-sphere. Two-sphere is not a group manifold, so this seems to fly in the face of what I was telling you before. However, there's a very nice way to understand this. So firstly, if you look at the truncation ansatz from this theory, it's extremely messy. Again, it doesn't seem to have anything to do with the group manifold I was telling you before. But it turns out there's a group manifold hidden. So we have a theory of a metric, a scalar, and a vector with a very specific coupling. And when you have this very specific coupling that allows you to do a consistent truncation, it turns out this theory can actually be unified into a higher dimensional theory of pure gravity. This is just the theory that comes when you take a gravitational theory and you reduce on a circle. Okay, so by unifying the gravitational field, Maxwell field, and dilaton field into a higher dimensional theory of GR, we get a simpler theory. And in particular, from this perspective, we now have a consistent truncation on some S1 fibration over S2. And if you look at the details, it's exactly the Hopf fibration. The consistent truncation is on a three-sphere from this high dimension perspective. The three-sphere, of course, is a group manifold. So having unified the Einstein, Maxwell, and dilaton field, we see that actually there was a group manifold in this unified picture. And in particular, from this high dimensional perspective, this unified perspective, we again have the same constituents like before. We have this globally well-defined frame. The vectors close into an algebra, and the algebra is exactly SU2. And this is why the lower dimensional theory has exactly an SU2 picture. And the truncation ansatz also very nicely can be rewritten like I was telling you, where you simply expand in this basis. Okay. But then again, there seem to be examples, known examples of consistent truncations that seem to go beyond this. There is the famous consistent truncation of 11-dimensional supergravity on a 7-sphere to a 4-dimensional supergravity theory. There's the other example I mentioned, type 2b supergravity on a 5-sphere. And these, again, don't seem to have some group manifold picture underlying them. So what is going on? What's going on is that, again, you have to think not just of the gravitational theory, but also take into account now the fluxes. So we want to unify the metric and the fluxes of the supergravity theory into some larger theory, just like before we did with Einstein-Maxwell-Dilaton in a higher dimensional theory of GR. And this is exactly what exceptional field theory does. So take, as an example, 11D supergravity on some 7-dimensional compactification. 11-dimensional supergravity as a metric, a 3-form, and a dual 6-form. And I can now just repackage all of these fields together into some larger geometric structure. So if I do this with all the fields on the compactification, I find that these end up parameterizing some coset space E7 over SU8, and this is what I call a generalized metric. Generalizes the usual metric to now also contain the fluxes. And we see the first appearance of this fun group, the exceptional group of rank 7. Bracket 7 is just some particular real form, the so-called split real form. SU8 is its maximal compact sum. But I can also look at the symmetries of my theory. So I have a theory of GR. So I have obviously diffeomorphism symmetry. So vectors generate diffeomorphisms. I have 2-form and 5-form gauge symmetries for these fields. If I put these together and count, I find that there's exactly 56 components, which I call a generalized vector field, and 56 is exactly the fundamental representation of E7. So I can repackage all my symmetry parameters into one object, which transforms into 56 of E7. And then similarly, just like diffeomorphisms are generated by a Lie derivative, I can now construct an object known as the generalized Lie derivative, which generates diffeomorphisms and gauge transformations parameterized by a generalized vector field. And this generalized Lie derivative has a form very similar to the ordinary Lie derivative. So along a generalized vector field, it has a transport term and a rotation term. But crucially, the rotation term is now projected into the adjoint again of this exceptional group E7. And if I act with this object on the generalized metric, for example, I recover exactly the diffeomorphism and gauge transformations of all of these fields. Okay. So now there's many puzzling things here, but there's one particularly puzzling object I've written in here, this partial M. So capital M was for me this 56-dimensional index of E7. So what do I mean by a derivative along these 56 directions? I just mean the ordinary derivative along the 7 directions of the compactification, just embedded in the 56. So this is just some nice way of rewriting the derivatives along the ordinary 7 directions of the compactification in some E7-looking covariant way. So this is my fields, my symmetries. I can do more. I can rewrite the action. I can rewrite the full 10 or 11-dimensional supergravity action. So the Einstein-Hilbert term and the field strength of the fluxes squared. I can rewrite this and become a 2-derivative action with now the derivatives of the generalized metric. And moreover, because I have a notion of a generalized Lie derivative, I can talk about generalized tensors, I can introduce connections, and I can actually rewrite all of this in terms of some generalized Ricci scalar. So one can think of the 10 or 11-dimensional supergravity actions as some generalized Einstein-Hilbert action in this exceptional field theory.
So those fields depend on how many coordinates? Those M's.
So they depend on 7 internals and 4 externals in this case. So the 7 coordinates on here, 4 in here. I just make it look like it's 4 plus 56, but the other things are just nothing. All the fields depend on 4 plus 7 coordinates.
So what does Dij mean in practice?
Good. So I've decomposed here E7 under some general GL7 subgroup, which acts on this. If you do this decomposition, you find that there is a 7-dimensional representation, and then there's some 2-form or 5-vector representation, so on, just like the symmetry parameters. So I have vectors corresponding to this, 2-form transformations corresponding to this. But this is just the break-in. These things are all 0. This is just some formal object. It just means the ordinary 7 derivatives. So
But does that end up breaking the E7 symmetries?
yes, right. So E7 is kind of there. I write things in a way that is E7 covariant, but things are not actually E7 covariant. The coordinates certainly pick out some 7-dimensional subspace inside this 56. That breaks the E7. But we'll see the benefit of still rewriting it in this E7.
So right now, M4 and C7 are any manifold?
Any manifold. Any manifold I want. I'm just rewriting the theory. I'm just grouping objects together on C7.
C7 is compact.
It doesn't even have to be. But I'll be interested in C7 compact. I can do this with just some split. Okay, good. So finally, let me just say, I can play all of this game also for the type 2 theories. So what I have to change is how I embed these coordinates. So I would then have 6 coordinates and embed them in particular ways so that I end up with type 2a or type 2b. And I can also play this with other dimensions. So not M4 times C7, but maybe M5 times C5. Then I would get an E6 covariant formulation, etc. So the exceptional group will change, but the basic setup is the same.
I think I'm a little lost in the sort of big picture here, that I'm trying to make something look very symmetric, and then, but that symmetry is broken. Well, what's the?
The symmetry is strictly broken to some, it's called the geometric subgroup. It's like a GOD subgroup with some translations. The subgroup of E7 that would preserves this choice. So you can have like shifts of the zeros into here, and of course GL7 on here. But the benefit of unifying all of these objects is that we will see hidden structures that we didn't see otherwise. These are made manifest in this E7. But in particular, if I act with E7 on some background, I won't get another solution of the equations of motions, for example. Equations of motions break E7. Good. So let's see what this buys us now. Or Saf, did you have it? Okay. So let me come back to this group manifold picture. One benefit now is that I can recapture consistent truncations, particularly these examples that I mentioned of 11-dimensional supergravity on S7, type 2b supergravity on S5. I can capture these now in terms of a generalization of a group manifold to this picture of exceptional field theory. So what is this generalization? Well, before I had a frame on my group manifold. So now I want to have a generalized frame of this exceptional field theory. So this doesn't mean that the space has a well-defined frame, but it has a well-defined combination of frames and form fields and so on, so that it's well-defined in this E7 language. And then the second consistency condition I had was that the lead derivative of vector fields had to close into an algebra. This is now replaced by the generalized lead derivative of these generalized vector fields has to close into an algebra. And the structure constants in this case will define the gauge group of the lower dimensional supergravity theory. And if I have these two conditions satisfied, I can easily show that I can obtain a consistent truncation simply by expanding all the fields of the exceptional field theory now in terms of this basis of globally well-defined vector fields, generalized vector fields that I have. And the coefficients will be the objects of the lower dimensional theory. So what looks like a truncation on some complicated geometry with fluxes that seems to be miraculous from supergravity becomes much simpler once we do this rewriting in terms of exceptional field theory, and then we see this nice generalized group structure. Okay. Now this generalized group manifold picture actually has a technical name. It's called the generalized Leibniz paralyzable manifold. The generalized paralyzable is because I have this global generalized frame, so it's like a parallelized manifold, but in this generalized sense. And then Leibniz refers to the fact that this generalized Lie derivative closes into an algebra. It's not quite a Lie algebra, but it's something more general known as a Leibniz algebra. difference is not particularly important. Okay, so this way I can now capture all of these consistent truncations. And now I told you I want to talk about ADS CFT, so let me come back to what this means for ADS vacua. These consistent truncations can typically be defined around various ADS vacua in string theory, particularly around any maximally supersymmetric ADS vacuum. I can define a consistent truncation in this way. And so if I look at some, for example, ADS 4 times A7 solution, I can define some 4-dimensional theory that captures some particular subset of modes. But now I can deform the 7th sphere by the subset of modes. And in particular, I can end up with nice, interesting warp compactifications, which might have no bosonic or supersymmetries remaining, but which still form part of this consistent truncation. And so in particular, all of these still have this hidden group manifold structure in the exceptional field theory picture. And this will allow us to compute the Kaluza-Klein spectrum for these compactifications. Yeah. Any questions about this first part? Okay, so then let me show you how we can use this to compute the Kaluza-Klein spectrum for these different compactifications.
So does every marginal deformation of your starting gravity background preserve the structure, or not necessarily? This is some subset.
No, exactly. So this is a subset. Good. So I will tell you later about the generic case right at the end. But in this example, let's say we do ADS 4 times A7, we get a 4-dimensional n equals to 8 supergravity. This has 70 scalar fields. So if there are some exactly marginal deformations among these 70 scalar fields, then I would capture them. In this case, for A7, there are none, if I remember right.
So is the point that these three things that you're keeping are building into some larger E7 multiplet, whereas the things that you're discarding are in different E7 multiplets?
No, so indeed, the things I'm keeping essentially form an E7 multiplet. In particular, they parameterize this coset space E77 over SU8. The other stuff doesn't, I'll show you, also has some nice interpretation, but it's not quite E7. It really knows about the 7 sphere, so it'll be a mixture between E7 and SO8 structure. I'll show you in a bit all the other bits. Any other questions? Okay, so let me now show you how we can compute the Kaluza-Klein spectrum for these compactifications. So in the traditional picture, what you would do is you have some compactification, you'd write down a fluctuation ansatz around some background, and you'd expand your fluctuation in terms of a set of harmonics on your compactification. So in exceptional field theory, we'll do something quite different. We won't expand our fluctuations directly in harmonics, rather we'll expand them in a way that I'll make more precise in terms of the modes kept in the consistent truncation times the harmonics. And the benefit of this is that because the modes of the consistent truncation we can keep to full nonlinear order, this will allow us to compute the Kaluza-Klein spectrum for any vacuum inside the consistent truncation. So in particular, what we'll be able to do is we'll be able to do the harmonic analysis at the maximally symmetric point of the low dimensional theory, for example, the round phi sphere. But then because of this nonlinear structure of the consistent truncation, we'll also be able to compute the spectrum around some very deformed compactification.
So are you talking about the full spectrum or the spectrum just of modes?
Full spectrum. The full entire spectrum, not just the modes that we've kept. So and what's very nice about this is that these vacua of the low dimensional theory can still be very complicated. They're typically warped. They can break all kinds of bosonic and supersymmetries. And we can even do other things. We can even compute the spectrum as along the deformation. In particular, we could compute the spectrum along renormalization group flows.
How do you get the full spectrum from what you've done sort of?
I'll show you.
Oh, sorry.
I haven't shown
Yeah,
you
sorry,
yet.
sorry,
No,
sorry.
that's okay. This is just to explain the strategy. So how do we compute the full spectrum? Well, we'll use the fact that we have this hidden group structure on these backgrounds. So in particular, we have our set of generalized vector fields that gives a basis for all fields, because we had a global generalized frame. So we can use this to expand all of the fields in terms of some coefficients, which are now just scalars on the compactification. And then these scalars, we can simply expand in terms of a full set of functions on the internal space, what would be known as the scalar harmonics. So already the Kaluza-Klein spectroscopy story becomes much simpler. In the traditional approach, I would have to take all of my fields, for example, metric fluctuations, three-form fluctuations, and expand them in an appropriate set of harmonics. Metric fluctuations, I'd expand in some symmetric two-tensor harmonics. The three forms, I'd expand in a three-form harmonic. In exceptional field theory, because I have this generalized frame, I only need to expand in terms of scalar harmonics. So already the problem becomes simpler. And you can think of this a little bit as capturing the fact that the n equals to 8 supermultiplet contains all of the supergravity fields. So because this has somehow this n equals to 8 structure built into it, it should be enough to know about the scalar harmonics, which are related to the spin 2 field, and then the n equals to 8 supermultiplet will take care of all the other fields. So this is a sort of manifestation of that. But what's still quite strange is that we'll be able to use this for vacua that don't preserve n equals to 8 supersymmetry. Be able to use this for any vacuum.
I'm a little confused. So you're talking about deforming the internal manifold.
Yes.
So clearly you're deforming the metric.
Yes.
So why don't you need tensor spherical harmonics in order to describe what's going on in the supergravity?
Because essentially all of the internal structure will be captured from this generalized frame. So we can turn all of the tensorial structure into a scalar structure via the generalized frame, and we'll then be able to completely write any fluctuation as just a fluctuation of a scalar function in terms of generalized frame.
Is it a little bit like what one does in cosmology, where you end up decomposing the perturbations into scalar vector tensor perturbations of the geometry, and it's like you say you're only keeping the scalar perturbations and ignoring the tensor ones? Or
No, in this case really I can write the most general fluctuation.
I guess he has an a priori preferred basis of vector fields in the manifold. So he just contracts and he just expands everything in that basis. And since that basis transforms well with respect to some symmetry, it simplifies things a lot.
So it's not saying that you have some deformations of the geometry which are where the tensors are like derivatives of some scalar?
This is completely general deformations I can write in this way. I'll show you the fluctuation ansatz in just a sec, and maybe that will help.
Okay.
I guess those U's are a basis for the tangent space at every point.
This generalized tangent space.
Yeah.
Not the honest tangent space.
So any tensor could be expanded in them.
Then I just need to care about the fluctuations of the coefficient, but that's a scalar function.
Okay. But that sounds too general.
So I can do this whenever I have this global. So like in ordinary GI, I'd be able to do this on a paralyzable space, which of course would be a very boring compactification.
Yeah.
What's nice here is it only has to be generalized paralyzable, which can be very interesting compactifications. But I can't do this if you don't give me this global generalized frame. And I can't use this technology.
Okay.
Not in this incarnation at least. Okay, so let me just indeed show you this fluctuation ansatz. I told you the metric 3 form 6 form are in the generalized metric, and this parameterizes the coset space E77 over SU8. So if I now want to write down a fluctuation, I can write it in the following way. The background would be delta AB contracted with my generalized frame. And now do a small fluctuation. Because this object had to live in a coset, this thing is algebra valued. B algebra E77 minus SU8. So in this case, these are obviously scalar fields on the internal space. If I only let them depend on X, the lower dimensional 4D coordinates, this would be just the modes of the 4D consistent truncation. A general fluctuation will also depend on Y, but I can simply expand my Y dependence in terms of the set of scalar harmonics because they give me a full set of well-defined functions on my internal space. So I can write any fluctuation on the internal space in this form as something which for fixed sigma lives in this coset algebra E77 minus SU8. And now you see what I've been saying so far. This has a little bit the form of living in the consistent truncation. These first two indices are like the modes of the consistent truncation, E77 minus SU8, times the set of scalar harmonics. And what's very nice is not just that, well, we have this way of writing a general fluctuation in terms of just scalar harmonics. What actually happens is because all of these objects are very nice, we have this generalized group structure on these frames, and these are just some nice set of scalar functions, we'll immediately be able to compute the masses for any vacuum of the lower dimensional theory. So to do this, we just need two pieces of information. The first is information provided by the lower dimensional supergravity theory. And this is just the algebra that the generalized vector fields close into. So these structure constants of the algebra, X, A, B, C, these are known as the embedding tensor of the 4D theory. They would determine, for example, the masses of just the 70 scalar fields of the lower dimensional theory. But now we need to supplement this lower dimensional information with some higher dimensional information. And again, this is very simple. This is going to be just the action of the generalized vector fields on the scalar harmonics. I call this action some matrix T A sigma omega. And because of these simple differential relations, one can plug this now into the linearized equation of motion and immediately obtain an algebraic mass matrix, for example, here for the scalar fields. So,
Sorry, what were the IJ indices again?
exactly. So the I haven't introduced yet. So before I had these AB indices, which were like in this coset, E77 minus SU8. I just replaced this.
AB are like frame
56,
directions?
yeah, frame directions. The 56 frame directions. And now these had to be symmetric, which was this coset condition. I just write this symmetric pair now as an I, just to simplify notation. So I now obtain a mass matrix for all of the scalar fluctuations. So for these 70 times scalar harmonics fluctuations, it has three parts. The first bit you see does nothing on the scalar harmonics. It only acts on the IJ indices. This is just the mass matrix of the four-dimensional supergravity theory.
Scalar means scalar in space-time?
In 4D space-time. So scalars from the lower dimensional perspective. This would be the Kaluza-Klein masses of the four-dimensional scalars. So this lower dimensional supergravity mass matrix is just determined by X. It's some quadratic combination of X's. If you just compute the mass of this will give you the masses of the 4D fields, the 70 4D fields. Then you have a bit which does nothing on the lower dimensional supergravity index and only does something on the harmonic. That's actually just, this acts exactly like the spin 2 mass matrix does on just the scalar harmonics, and it's given as some quadratic in these T operators. It has the form of something like a Casimir operator. And then finally, there's some mixed term which acts both on the supergravity indices and the scalar harmonics. This is where all the fun happens. So this is the key object. It's some combination of the X and the T tensor. Okay, so we have this very explicit algebraic mass matrix that we can now use to compute the masses for this full set of Kaluza-Klein fluctuations for any vacuum from the consistent truncation. And so in particular, what's very nice is because we are nonlinear in the consistent truncation, we can just do the harmonic analysis, just find the scalar harmonics at our maximally symmetric point corresponding to the round sphere. And then all of the deformation of the round sphere is just captured by information from the consistent truncation. So in particular, we don't need to compute scalar harmonics on these deformed spaces. We're just going to use the scalar harmonics on the round spheres. And all this information of the deformation will be captured in some very nice way by just appropriate matrix multiplication by some E7 matrices. Okay. So we need to summarize the technology. We'll only have to compute scalar harmonics of this maximally symmetric point, which is typically some round sphere. The Kaluza-Klein ansatz in exceptional field theory turns all of the differential problems into algebraic problems. We have a mass matrix with some finite dimensional matrix whose eigenvalues we can now compute. And in particular, we can use this to compute the full spectrum for any vacuum in the consistent rotation. This includes interesting compactifications, which may have no symmetries.
Sorry, can you go back? I think something went too fast. How did you get the truncation to a finite dimensional space? That was by fixing what? So you had an algebraic finite dimensional matrix.
Sorry, good. So this is just saying that I can fix my Kaluza-Klein level. So the Kaluza-Klein level grades this set of scalar harmonics.
What is the meaning of level?
So
setting?
In this case, the round sphere. So I have the round sphere, let's say I do S7.
Okay.
In S7, the scalar harmonics transform in the representations N0, 0, 0.
Sure.
It's the symmetric, traceless, N4 polynomial.
Okay.
This is the Kaluza-Klein level.
Okay.
This is what I used. And for fixed N,
then you get a finite dimensional.
I get a finite dimensional matrix. And in particular, it doesn't mix different N's.
Yeah.
Any other questions? Okay, then I'll reward you with sitting through this technical part and show you some applications. So now we can do this, we can review the Kaluza-Klein spectrum. What can we learn? In particular, I want to show you two sets of examples. The first is studying stability of non-supersymmetric ADS vacua. And the second one will be about learning about these global properties of the conformal manifold. Okay, so we can obviously use the technology to study non-supersymmetric vacua. If I have a consistent truncation with some non-supersymmetric vacuum, I can just go ahead and compute now the full KK spectrum. And of course, what's very interesting is that these non-supersymmetric vacua could be unstable. In particular, they could have perturbative instabilities, which just means that some of the masses square to negative numbers, or in the case of ADS, they have to be negative enough to trigger an instability. They have to lie underneath the Python-Friedman bound. Now, most non-supersymmetric ADS vacua actually are unstable already inside the consistent truncation. So if I do a consistent truncation to 4D, typically some of the 70 scalar fields that I keep will already trigger instabilities. For all but a very small set of non-supersymmetric solutions, this is true. So people used to believe that, while we don't have scale separation, the modes that I keep in the truncation are usually the lowest, in the sense that all the higher modes are at least as heavy as the modes that I've kept. So if I have stability amongst the modes that I keep, there should also be stability amongst the higher modes. This used to be a belief. Given that there are so few non-supersymmetric solutions that don't have instabilities amongst the zero modes, maybe the zero mode stability is enough. So this we can test now. If I look at the consistent truncation of 11D supergravity on the 7th sphere, I get some nice 4D theory. And there's actually only one non-supersymmetric ADS vacuum that is stable in the 4D theory. There's many, many non-SUSY ADS vacua. All of these, learned by machine learning, are already unstable in 4D except for one single vacuum. This one vacuum deforms the 7th sphere in some complicated way that only preserves SO3 times SO3 symmetry, and now we can compute the spectrum and see if it's stable. Okay, in particular, we can test this idea that people have is the stability amongst the modes that we've kept enough to ensure stability of the higher modes? And so here are the results. I'm showing you the KK spectrum. On the y-axis, I have the mass normalized relative to ADS. This is the multiplicities written as representation of the symmetry group, SO3 times SO3. And this red line is the Bright-Noner freedom bound. So stuff above is good, stuff below is tachyonic. At level 0, I have the 4D supergravity fields. I'm only showing you the lowest lying modes. As I said, these are all stable. So everything is above the Bright-Noner freedom bound. And now we can compute what happens as we go higher up in the KK level. And already we see something interesting. At level 1, we get lower lying modes already. So this is already interesting. But they got close to BF bound bias just above. But then at level 2, things go bad. We end up having tachyons. So at level 2, you already find modes that trigger instabilities. So having 0 mode stability is not enough to guarantee stability amongst the full 11D supergravity. And we can continue computing. We did this up to level 6. And we find that eventually the masses do seem to increase with KK level, at least not at first. So
these modes do what?
Sorry?
These modes do what?
They're tachyons. So they trigger.
Yes, they're tachyons, but what do they deform something? What do
They deform the 7th sphere in some complicated way, but we haven't worked out kind of the end point of the instability, if that's what you're asking. We could in principle, but we haven't done so. In principle, one could try and see where these modes lead. Okay. So what's nice is already we see that higher Kaluza-Klein modes can become unstable. So even though modes you've kept in the truncation are stable, you find instabilities. And in particular, there is some perturbative instability of this non-supersymmetric vacuum.
Do you have any intuition as to why the low L modes are stable, but the high L modes are unstable?
No, we'd love to somehow. What we haven't yet got around to is really looking at the mass matrix and trying to work out what is it that determines when something is stable or unstable without going through this procedure of actually computing the results.
But at least the asymptotics for large K in the previous plot, can you
Yes.
say that it will
Exactly.
go up at some predictable
Exactly.
speed for large enough K?
It seems to. We only computed up to level 6. This was in the early days when we didn't have very efficient code, but they certainly seem to increase. With mass, at some point, they do seem to just get higher and higher. So it seems to be that if you have tachyons, they should be in the first couple of levels, but we don't have a proof.
In that sense, right? When you're very highly excited, you don't know about all the features of the geometry.
Yeah.
Right, but of course, you have a very strange notion of KK level, right? In principle, the KK modes could become somehow because you have an elliptic operator that's bounded. I think you know from math that you should have only finitely many excitations with eigenvalues below a certain bound. So you should be able to show that these masses can't become arbitrarily negative. Presumably at some point they either asymptote to some constant unstable value or they increase. Yeah, we haven't studied this in more detail yet. Okay, let me come back to some supersymmetric examples now. Yeah.
So what's the takeaway for the non-supersymmetric vacuum?
The takeaway is this particular example is unstable, and it's unstable in a sense in a surprising way because the 4D supergravity seems to suggest it is stable, but higher KK modes that one usually thinks of as being heavier are actually more unstable and trigger instabilities.
And that was the only one.
This is the only one in this consistent truncation that had any chance of being perturbatively stable, and it's unstable. I will come back to this and show you some examples of perturbatively stable non-SUSY vacuum.
But higher KK modes typically represent higher momentum modes in the X-ray. How can it be?
Well, exactly. So I think that is a wrong picture to have. Indeed, asymptotically, that is true. Asymptotically, we see that these masses seem to increase, but at least at first, they go down. So if you want, the notion of level is, in some sense, not a good one. You don't have a scale separation. You can't use the intuition. As I said at the beginning, the 4D supergravity picture can be very misleading.
So what's the horizontal axis in these plots?
So this is
the
actually
representation of SO3 times SO3. So it's a very, I mean, the internal manifold doesn't preserve all the symmetry, which I think is why it's breaking the intuition. Like it's a topologically S7, right,
Exactly.
which would have had SO8. On the round metric, it's certainly true that increasing the level would increase the energy. But if you have a metric that only preserves SO3 times SO3, then maybe there can be something that's not even charged under that, but that is kind of going negative in a sense.
And yeah. So this is just a multiplicity essentially, which is related to the KK level as well. So yeah. Okay. So let me now turn to some ADS CFT application, this question of the conformal manifolds and supersymmetric examples. So there's an interesting set of n equals to 2 ADS4 vacua, which arise in some particular 4-dimensional supergravity model. So this is some particular gauge group. The details are really not important. What's nice about this is there is a 2-parameter family of n equals to 2 ADS4 vacua. So I have 2 parameters, phi and delta. For any value of n equals to 2 ADS4 vacuum, so this would be holographically dual to some n equals to 2 conformal manifold. But then there's also some puzzling features. In particular, the parameters phi and delta seem to be non-compact in the 4D theory. They seem to take any positive value. And the 4-dimensional ADS4 vacuum seems to be different for any of these values. Particularly the masses of the 4D fields that you've kept change and have no periodicity in phi and delta.
Why is that puzzling?
Why is that puzzling? It's puzzling because there's various claims in the CFT literature, for example, recently by these people, that the conformal manifold should be compact. So on the one hand,
about any a 3-dimensional superconformal theory. I mean, there's not that much evidence to support that thing. So
that's true.
in other dimensions, it's definitely not compact.
Yes. So yeah, there's this lore that somehow, if you have no weak coupling points, the conformal manifold should be compact, and there should be no weak coupling points. So somehow the conformal manifold should perhaps be compact. Let me show you what happens. I will be able to show you that at least one of the directions is compact. So this family has some other nice features. Generically, it has some very small bosonic symmetry, U1 times U1, but its special points, the bosonic symmetry and the supersymmetry.
And what's the metric on the phi delta space in the kinetic term fields?
It's some hyperbolic space, if I remember right.
Is it finite volume?
No.
It's not even finite volume.
It's not even finite volume. If I remember right. I'll check later and let you know. Okay, so the first thing you could say is, well, maybe there is no puzzle, maybe this is some 4D supergravity theory, it has nothing to do with string theory, it's not UV complete, you shouldn't really be using ADS CFT. However, we can uplift it via consistent truncation. It was done by these authors. And so actually this n equals to 2 family corresponds to some family of S5 times S1 ADS4 vacua, which are on this type 2B string theory solutions. They are known as so-called S4 vacua. You can ask, but I'll say maybe at the end some more about this. So we now have this picture where for any value of phi and delta, we have one of these vacua. In particular, people uplifted these special points where the bosonic and supersymmetry arises. So then to understand compactness, we took one of these directions, the phi direction is slightly nicer, and simply studied what happens to the KK spectrum as we vary phi. So we can do this now. And so here is the part of the result. So we compute the spectrum along this phi direction. So for any value of phi is plotted here. We have an ADS4 vacuum. And on the vertical axis, I have the mass of some particular field that I'm looking at. And these are the modes which are Kaluza-Klein level 0 on the circle. Okay. We see some of the modes become heavy as we change this phi, some modes don't care about phi and are constant. And now we can compute this also at the first level. And then you start seeing, okay, there's some more heavy fields. nothing seems to particularly change. But we can keep going up in the circle, and we start seeing that some of the higher modes on the circle, which were heavy for phi is 0, become lighter as phi increases. Some become very light. So if we increase this picture up to level 10, you really start seeing that more and more heavy fields become light as we increase phi. And in particular, the whole structure seems to become very symmetric around this point here. And in particular, we can show the Kaluza-Klein spectrum is the same at this point as at this point, and the KK spectrum preserves this periodicity. So the KK spectrum gets mapped back to itself whenever we shift phi by some multiple of 2 pi over t, where t is the radius on this S1.
But if you have this analytic solution, can't you just tell whether shifting phi by this 2 pi over t is the same solution or not?
Yeah, so we will come to that. You can. The reason why people didn't do this immediately is because it's actually very hard. So typically, even though in principle you can, uplifting can be very difficult. Some people weren't very interested. They were like, well, it's some random deformation, who cares? But indeed, motivated by this, you should now go away and check what happens to the compactification. Okay. So let me tell you about that in a sec. We have a very nice picture now where higher Kaluza-Klein modes become light, and in particular massless, whenever phi is an integer of pi over t. In particular, along this axis, you get points of bosonic symmetry enhancement coming from the higher KK modes that you didn't have in the 4D theory. So in particular, you get this enhancement from U1 to U1 times SU2 times U1, but the full spectrum is the same whenever you have an even integer times pi over t, and it's different when you have an odd integer of pi over t. You still have this bosonic symmetry enhancement that you didn't see in the 4D theory. Okay, so from this perspective, this non-compactness of the phi direction seems to be a 4D artifact. 10 dimension, it actually becomes compact. And what happens is that higher KK modes replace modes that became heavy. Okay, now we can also compute the full KK tau as a function of phi. I just wrote down the result to show you that we can. This is the conformal dimension of the conformal primary, superconformal primaries. And this is as a function of various charges, like U1R charge, the Lorentz spin, the SU2 symmetry we had at the start, the S5 level, the S1 level, etc. Okay. Playing the same game along the other direction, however, doesn't seem to show compactness. The KK spectrum is certainly not periodic along the other direction. Okay, so now let me come to your question.
Doesn't that falsify this conjecture?
Yes, or you might say perhaps the KK spectrum isn't enough to look at. Maybe you need to go beyond supergravity to see compactness. So within type 2b supergravity, there's no compactness.
But can't you truncate isn't the low energy limit self-consistent?
Not terribly clear at this point. You have vanishing circles. You have some circles that become tiny. The dilaton gets quite large. So there's reasons to believe that you shouldn't be doing type 2b supergravity anyway.
So is there some statement that there's some remnant of some kind of U-duality symmetry that you're supposed to quotientify?
Yeah, good. So you can, one way of interpreting this is that you should think of this 4D theory as having some duality symmetry that relates this line to this line. This, yeah, you could say that. Again, it's very hard because this isn't actually low energy theory, so it becomes a little bit difficult to make these statements. I'll make the statements that I'm confident in, which is that these KK modes become light.
And the topology is what again?
Good. So the topology is S5 times a circle. And I can actually now also tell you what Clay was asking. Can you not just see this from the geometry? That is the same space. And you can. With this motivation, we went away and really did the uplift, and it's a bit complicated. So you take the S5, the symmetries tell you to really think of the S5 as some 3-sphere warped over a 2-sphere. And then you take the Hopf fiber on the 3-sphere, combine it with this S1, that gives you a T2 vibration over S2. Then you can understand this modulus as a complex structure deformation of the T2, particularly corresponds to this real part. And that is indeed a periodic modulus. When you shift this by 2 pi over t, tau shifts by a Dane twist. So then indeed you see, yes, the geometry clearly is compact. The compactification is the same whenever you do the shift.
And what's the delta in this?
The delta is some horribly complicated deformation that, yeah, it's very nasty. So various, as I said, some circles seem to shrink, some seem to become large. The dilaton blows out, it's nothing nice. Okay, so one thing I do want to point out, because I'll tell you in a little bit about some non-SUSY vacua that are very similar, is phi deformation. Different way of describing it is as corresponding to locally a coordinate transformation that can't be made globally well defined. That's how you can think of the T2 complex structure. You can think of this as a deformation of the metric that could be removed locally by coordinate transformation, but the coordinate transformation isn't globally well defined. Okay. So in particular, there's actually 2 other flat directions in the 4D supergravity that break SUSY. So this background seems to connect to some non-supersymmetric moduli space of ADS4 vacua. So here we have the n equals to 4 point. This is this n equals to 2 line that we studied. And then for generic values of these 2 other directions, chi1, chi2, we end up having no supersymmetry. So this seems to suggest maybe there's a non-supersymmetric conformal manifold, but this certainly isn't expected to exist. There's no reason why, even if you have marginal deformations, this would be exactly marginal. Typically expect that you need some sort of protection mechanism that preserves marginality in the full quantum theory. The supergravity suggests that maybe there is such an example. Okay, so in particular, I'll show you, we can show that this non-supersymmetric conformal, this space of non-supersymmetric X vacua is perturbatively stable. It seems to be non-perturbatively stable, and also it has some very nice features which protect it against 1/n corrections. So this has to do with the fact that these deformations are locally coordinate transformations, but which are not globally well defined, very similar to the Dane twist of the torus. Okay. So firstly, the perturbative question. We can just apply our method. We can compute the full KK spectrum. And here's the result, not to particularly take in, but just to show you we can do it. And in particular, we can show that all of these masses are buffeted by a monofree buffer. So perturbatively, these non-SUSY vacua are stable. And there's the question of non-perturbative stability. This is very difficult, and we can't make definite statements, but certainly a probe brane analysis suggests that actually, if you put a probe brane in, the tension is greater than the charge, and the vacua actually seem more stable than the supersymmetric point. In particular, there's no sign of the instability that Oguri and Buffer predicted in 2016. You can ask about Witten bubbles of nothing. The circle and the S5 are protected against these. Those don't seem to happen. And more recently, in a different class of non-supersymmetric vacua, a bunch of people suggested some mixed kind of bubble of nothing with a D brane could exist. This could also happen here. We don't know. But certainly the simple kind of non-perturbative instabilities that were conjectured to exist don't appear here.
What was specifically the Oguri-Vafa instability?
The Oguri-Vafa instability says that whenever you have a flax compactification, there should always be some brane with charge greater than tension. So this will nucleate and then expand and carry away some flux and eventually decay the vacuum to something else.
This looks like a moral violation of weak gravity.
Yeah, but yes, but somehow the weak gravity argument is very much based in a low energy effective action kind thinking. Again, you don't have a 4D low energy effective action, so I'm not sure whether you're really violating weak gravity or just abusing weak gravity in the wrong context.
What about lifting this moduli space by some kind of D-brane instanton?
I'll come to that in a second. Let me first ask about 1/n corrections. This is some of the large n limit of some CFT, maybe these factors get lifted by 1/n. In the supergravity, this will correspond to some sort of higher derivative correction. But this is where things are very nice. We have a protection mechanism coming from diffeomorphisms. Chi1, Chi2 can locally always be absorbed into a coordinate transformation, which means that any kind of diffeomorphism quantity, invariant quantity right down, doesn't depend on Chi1, Chi2. Riemann tensor, Ricci tensor, Ricci scalar fluxes, they cannot depend on Chi1, Chi2 because these things can be absorbed by some local coordinate transformation. But they're physical moduli because the coordinate transformations are not globally well defined. So this seems to protect against these 1/n corrections. And in particular, a very similar argument also applies to some n equals to 1 exactly marginal deformations found by these authors. ADS4 n equals to 1, also not meant to have, the 3D theory is not meant to have a conformal manifold for similar reasons. Okay, but then indeed, what happens to D5 instantons? You could imagine wrapping a D5 brain on S5 times S1. Certainly the classical part of that instanton action would correspond to volume S5 times S1, and again, this is independent of Chi1. And quantum fluctuations about this, I don't know. So of course, the instanton could again kill it. If I were a betting man, I would bet on some kind of instanton correction, because this would also kill this example, whereas non-perturbative instabilities wouldn't kill the supersymmetry example. So at least there seems to be a lot of protection. There seems to be a lot of very nice things happening for these non-supersymmetric ADS vacua.
Is G-string under control?
G-string is certainly small.
It's tunably small.
It's good. So, and again, it's somewhat nice. You're starting with some supersymmetric vacuum. You have flux quantization. Everything looks good. And you deform a little bit, and you have lots of nice things happen. Of course, various things could still go wrong. You could have these instantons. I mean, no one knows how to compute these instanton corrections. They could kill it. Okay. Let me maybe just say a couple of words about some ongoing work. This was all to do with how to compute the spectrum around compactifications when I go to a different vacuum inside the same consistent truncation. And we can actually also apply this to different deformations which go outside the consistent truncation. So if I think about 4D, the truncations to 4D, I'd have 70 scalar fields corresponding with some vacua in the 4D theory. More generally, I could consider some different deformation that takes me outside the space of 70 scalar fields. Well, it turns out we can also capture these kinds of deformations. So this would now correspond to some generic RG flow n equals 4 super Young Mills, for example. This would contain exactly marginal deformations of, in this case, ADS5 is 5. You could play the same game with ABJM, of course, on ADS4 is 7. Right. So what's very nice about this is, because you're still in the same topological space, you still have this property of generalized paralyzability. So you still have the global set of generalized vector fields, but the generalized Lie derivative of this doesn't close into an algebra with constant coefficients now. The coefficients depend on 1. But many of the things are still true. You only need scalar harmonics. Let me just tell you, we can now use this, and in particular, we're working on 2 particular examples. One is essentially finished. We can compute the spectrum around the ADS4 times squash 7 solution of 11D supergravity. We can look at the beta deformation of ADS5 times S5. And yeah, let me end it there with a brief conclusion. So I've shown you how we can use this technology coming from exceptional field theory to compute the full KK spectrum for an interesting class of mobile compactifications. These can have no remaining symmetries or supersymmetries. We learned a bunch of things about some nice effects in physics that I won't repeat again. I'll just mention we have some more examples of perturbatively stable non-SUSY ADS vacua in massive type 2A that I didn't talk about. These are isolated points. Again, they're perturbatively stable. And finally, something I didn't talk about is the sort of bread and butter ADS CFT checks. One can compute the spectrum. We can look at the short multiplets compared to symmetric indices. We do this with some people. And then finally, you can also push this to some more things. So for example, you could ask, what about 3-point functions in the CFT rather than 2-point functions? What about more general vacua? Can one maybe go beyond ADS? Anyway, I'll leave it here. Thank you very much.
Any quick questions?
Longer questions.
Okay, we had quite a few during the talk, so let's just thank Emanuel again and
I guess maybe you could do this in cosmology. It just, I mean, yeah, I mean,
they're interested in this one.
the total space is parallelizable, which probably it is. It's like